So I'm going to present some preliminary results of my recent study on Apollo 14 impact breccias and trying to see whether these impact breccias we recorded two impact events. On the left side, you can see one of the thin sections that I'm currently analyzing, and highlighted are the grains of interest. So in blue, you can see phosphate grains, and in pink, they are the zircon grains highlighted. And in general, zircon phosphate grains occur widely as SSR minerals and planetary materials, not only lunar breccias. The sizes range from less than 10 micrometers to up to 500, at least for some zircon grains. Phosphates are normally a bit smaller, but at least they're large enough that we can place like single spots or several spots within one of these grains or several of these grains and date these grains. And that is why uranium lead dating of these minerals is now an important tool to understand the impacted magmatic history, for example, of the moon. And just a bit of background, because we have now talked a little bit about zircon and phosphates before already in the talks. So why do we use zircon and phosphates actually for these datings? So we want minerals that include uranium but exclude lead in their crystal lattice. And that is exactly what zircon does. Also, it has a high closure temperature of the uranium lead system, around 900 to 1000 degrees, which makes it highly resistant to thermal disturbance. So if we date these zircon grains, normally we get primary crystallization ages. And for example, we can tell with these ages that we can get information about the magmatic history of the moon. On the other side, we have phosphates. They have a low closure temperature of the uranium lead system, around 500 degrees, which means that the uranium lead system is prone to resetting during a thermal event, for example, an impact event. So the assumption is here, if we date these phosphate grains, if they were completely reset during impact event, that we actually can date these impact events. However, in some cases, we think that maybe these phosphate grains were not completely reset, but just partially reset. And this will give us some wrong ages or like meaningless ages. And that's where it's important, what we also heard before, we really need to look into microstructures of these grains because they may provide some additional information that is very important when we interpret these obtained uranium lead ages. And just showing here some previous studies. So for zircon, they have been studied in the past more extensively. We have seen some shock features in zircons before, and for example, some plant deformation fractures. And here's just an example on the left side also of a medaillate grain studied by White et al. We can see the disorientation of the grain, which is not visible in the backscatter image and only in EBSD. Then there was a study by Anna Chernak et al. In 2019 on some Apollo samples as well, on some phosphates and some Apollo samples, and a study by Kenny et al. On some terrestrial phosphate grains. And we can see actually like in the backscattered images, we don't really see any like signs of deformation or misorientation of these grains. But just if we look really into the microstructure, so it's EBSD, we can see that these grains are actually quite deformed. And this is quite important to know when we get the uranium lead ages out of these grains. However, how shock deformation as a result of an impact event leads to incomplete resetting of the uranium lead system and phosphate and zircon is still not really understood. So that's why, I chose to look at the Apollo 14 landing site and some breccias over there. Highlighted here is the Apollo 14 landing site. Shown here is as well the Imbrium impact basin. And here's just, we've seen this before on the landing site of the Apollo 14. And I'm analyzing 7 different breccias. 4 of these were sampled close to the landing module, and 3 of them were sampled within the continuous ejector blanket of the cone crater. And some of these samples have been analyzed before, not all of them, but some of them. And actually we saw in the phosphate ages, we saw 2 different ages so far. So we saw one younger age of 327 million years and one older age of phosphates with an impact breccias closer to the cone crater around 3940 million years. So the idea is that maybe these impact breccias actually recorded 2 impact events at the Apollo 14 landing site. And this has been interpreted as a possible mixing of Imbrium ejecta with older material that might be underlying the Fra-Mauro formation at the Apollo 14 landing site. And that's maybe was excavated by the cone crater impact event. And this, again, what we've also heard now before, leads back, of course, to the question, if we see these 2, if there's really 2 impact events recorded in these breccias within this narrow time interval of 10 to 15 million years, then this brings us back to the question whether there was a late heavy bombardment or even cataclysm around 3.9 billion years. So I'm showing now some first results that I've got. So only phosphate grains within breccia 14311 were large enough for age dating. That's the only breccia I could actually date for. The grains in there are around 20 to 100 micron in size. Some of them grow poikilotic. On the left side, you can see I have some poikilotic intergrowths with other minerals, which means they crystallize probably at the same time. The zircon grains are normally like as fragments within the matrix, and they are anhedral and around 10 to 120 micron in size. And some of these zircon grains also show some features in cathodoluminescence imaging, just like some features that we can see over here, some zoning. Then I also did some EBSD analysis at the University of Portsmouth. And here's just an example of one cogenetic merylite apatite grain seen in the secondary electron image over here, also nicely seen here in the CL image. And the band contrast image does not reveal any signs of shock deformation of phosphate or zircon. Also, like I analyzed the zircon grains as well, or any kind of deformation or misorientation of the grains. And this is not only true for this grain, but for all of the grains that I've analyzed. I couldn't see any deformation or anything, showing me that. Quite surprising, because these are all impact breccias, and they must be quite shocked. However, what I saw and what I've not seen before in any of the impact breccias are these interesting merylite grains. I saw some features that I saw on the secondary and also in the backscattered electron image, also visible in CL, and just here's a zoom in. So I saw these kind of fractures, and also visible in the band contrast image again. Again, no signs of deformation or any misorientation within these grains. And here's just another example of these merylite grains. And first I thought maybe it's due to polishing, because these samples were polished for EBSD and phosphates are quite soft. Maybe something got polished away. Then I wasn't sure what's really fractures. There was maybe some chemical variations, maybe some exsolution lamellae. And it's just, I only see the merylites, not in the apatite grains. That is shown over here. So here's again another composite merylite apatite grain. The merylite shows again these features in CL and the secondary electron, and also in the band contrast image, but I cannot see these features in any of the apatite grains. And then, I got my first results for, like I said before, only phosphates in breccia 14311 were large enough for age dating. I got an average age of 3941 million years, which fits nicely from a previous obtained age from Merle et al. In 2014. He received an age of 3938 million years. So within, the error is the same. And again, we've seen this age also before for Imbrium. This is actually phosphate grains within different impact breccias from 5 different landing sites gave this age. And only the outliers are these phosphates from these 2 samples. Also, I couldn't see any age difference between merylite and apatite grains. And for the zircon grains, the ages range from 3.94 to 4.33 billion years. And the only zircon grain that is pretty young, that gave me this age of 394, is from impact breccia 14321, also within the continuous impact ejector length of the cone crater, and nicely fitting within these older phosphate grains. So far I can just confirm this older age. I didn't see any younger ages, but I have to continue dating the other breccias. And this brings me actually to my future work. So I received some new syn sections, which I'm currently analyzing. I've seen as well those merylite grains in 2 of the syn sections at least so far, so I'm looking for them now. And I also got replacements for the other syn sections where the phosphate grains weren't large enough for age dating. So I hopefully find some phosphate grains in these that are large enough for dating. Also, I want to do some ion imaging of these grains, like of this phosphate and zircon grains, to see the distribution of thorium, uranium, lead in these grains, just to see if there's any accumulation in some areas of lead or uranium that could lead to some older ages. And of course, I would like to study the observed lamellae. I call them now lamellae at the moment, in merylites, for example, by transmission electron microscope. But I'm happy about additional suggestions because, I've talked to many people about these now already, wherever I went with my thin sections, but no one has seen these features before. So if anyone has ideas, I'm happy to get ideas. And that's it. Thank you.